So in this video, I'm going to talk about the indeterminate forms, all of the exponential ones. All of these go together. So you can do 0 to the 0, which again, it's an indeterminate form because 0 to any power is 0, but anything to the 0 power is 1. So it's kind of conflicting information there. The same idea as this one is if you raise infinity to a power, you should get infinity, but anything to the 0 power gives you 1. Definitely conflicting answer there. Same idea here is if you have 1 to a power, it should be 1, but if you have something to the infinity power, it should probably be infinity. So we've got a confliction there. And so that's where all of these indeterminate forms come from, is some kind of conflicting bit of information. So what we're going to worry about here is this limit as x goes to a of f of x to the g of x. So we've got f of x as our base and g of x as our exponent. The trick is going to be with this one is rewriting it as a slightly different problem. So what I'm going to do is I'm going to actually write it as e to the g of x times natural log of f of x. And so what actually is going to happen here is you notice this e and this natural log are inverse operations of each other. So that's the idea of what's going to happen here is this is going to essentially cancel each other out. F of x is going to become the base again, and g of x is going to stay in that exponent. So the trick here, though, is going to be, and I know I see a lot of textbooks write it this way, is instead of writing it as e, they write exp and put in parentheses g of x times ln of f of x. And so basically the process here is going to be focusing just on what's in these parentheses, just on that exponent, and then the last thing we're going to do is raise it to a power of e. And so this part right here in this parentheses, this argument, g of x times the natural log of f of x, is going to end up being what we use as our L'Hopital's rule. This is going to typically turn into some kind of a fraction in most cases, and that's where we can, apply L'Hopital's rule. Because again, L'Hopital's rule requires the use of fractions at some point in some way. So I'm going to go ahead and look at my first example here, which is the limit as x approaches 0 from the right of 1 plus sine of 4x to the cotangent of x power. So again, just to verify that this does in fact have one of those indeterminate forms, sine of 4 times 0 is going to end up being 0. So this is going to be a 1 as my total argument on the inside here. And the exponent here, cotangent of 0 from the right, is actually headed toward positive infinity. So again, this is in fact one of those indeterminate forms. So what we're going to do, again, is try to rewrite this limit using that special form. So I'm going to still write it as limit as x approaches 0 from the right. And the way I'm going to write it is e to the cotangent x times ln of 1 plus sine of 4x. And so that's going to be how I rewrite this to make it all work out nicely. So what I'm going to try to do with this particular problem is, again, I just want to focus on what this exponent is. I'll save this e for the very last step. So what I'm going to do is I'm going to worry about limit as x approaches 0 from the right of cotangent x times the natural log of 1 plus sine of 4x. So what I'm going to do here is I'm going to rewrite that as a fraction. Now, I'm probably going to move this cotangent of x to the denominator, which is going to make it tan x. And that way I'm going to leave that natural log of 1 plus sine of 4x by itself in the numerator. And so now I can apply L'Hopital's rule, because again, L'Hopital's rule does require the use of fractions at some point in some way. So I'm going to take the derivative of this. I'll probably do the tangent first because that's pretty easy. Tangent of x's derivative is secant squared of x. And if I take the derivative of this thing, the natural log of 1 plus sine of 4x, well, I'm going to have to involve the chain rule. First part is it's 1 over what's in the parentheses, the 1 plus sine of 4x. And then I'm going to multiply that by the derivative of what's inside. Well, 1 turns into 0. Sine is going to become cosine of 4x. And then I got to do the chain rule again because that 4x got to multiply by 4. All right, so lots of stuff that I have written down. Let's see what I can do to kind of make this a little bit simpler. Let's see. So that's going to be cosine of 4x times 4. So I'll write it as 4 cosine of 4x. And let me go ahead and rewrite a few of these things while I'm sitting here thinking about it. So we've got 1 plus sine of 4x. That was in a denominator, so I'll keep it in the denominator, 1 plus sine of 4x. And then we've got times secant squared x. At this moment, I kind of wonder what's going to happen if I actually plug in 0. What's it going to do if I actually plug in 0? So cosine of 4 times 0 is going to give me actually 1 times 4. So I'm going to write 4 times 1 over, let's see what happens. Secant squared of 0 is also going to end up being 1. Because it involves cosine. Secant is 1 over cosine. So that's still going to give me 1, even if you square it. Sine of 4x is going to turn into 0. So that's going to be 1 plus 0 times 1. So if I multiply this stuff together, we have 4 times 1, which is 4. And 1 plus 0 is 1, times 1 gives me 1. So that's 4. Now, I'll mention to you a lot of people on this problem get stuck here. They forget that originally this was an exponent. So what you need to watch out for here is, again, going back and saying, you don't even need to write the limit as x approaches 0 anymore, but it was e to the cotangent of x times ln of 1 plus sine of 4x. We figured out that that exponent was really a 4, so it's e to the 4th as the final answer. So again, people tend to get a little bit stuck and just say 4. But don't forget that it was actually an exponent. So that's going to be my final answer on this question, is e to the 4th. And I'll move on to another one. In this example, we have the limit as x approaches 0 from the right of x to the x. So again, please just verify that this is in fact the indeterminate form that we want. Well, x turns into 0, so does that exponent. So yeah, it's 0 to the 0. But again, we just want to verify this to make sure we use the correct method, or the fact that it does involve L'Hopital's rule. So I'm going to rewrite this again. Keep the limit. Limit as x approaches 0 from the right. And I'm going to rewrite this as e to the x, this x on the outside, times the natural log of x. The base x goes in the natural log. All right. So now that I've got it written this way, we need to try to rewrite that exponent, and that's what I'm going to focus on, as a fraction. And I know I already did this problem in one of the other examples, but I'm going to go ahead and focus on it again. So again, I'm just going to focus on x times the natural log of x. And I'm going to move this x to the denominator, so it's the limit as x approaches 0 from the right of the natural log of x divided by x to the negative 1. When I do the derivative, we have ln of x turns into 1 over x, which is x to the negative 1. And the derivative of x to the negative 1 is negative 1 x to the negative second, which takes me back down to negative 1 times x to the first. So this is going to give me 0. So what that tells me, again, people get stuck here. They say, oh, I found the limit. I've got a number at 0. But remember, back up here, we wrote it as an exponent. So focus on the exponent for a minute, but just don't forget that it was there. So it's e to the x times ln of x, which becomes e to the 0, which is actually 1. So my answer here is 1. Okay. All right. I got one more example. We've got the limit as x approaches infinity of 1 plus 2 divided by x to the x power. Again, please verify that this is in fact the appropriate indeterminate form. Well, if you try to make this x go to infinity, that's going to turn into 0. So it's 1 plus 0, which is 1, to the x as it goes to infinity. So we've got 1 to the infinity as our indeterminate form. So again, let me repeat. We want to rewrite this as an exponent. So I'm going to write the limit as x goes to infinity of e to the x times the natural log of 1 plus 2 over x. Okay, now that I've got that set up, I want to, again, just focus on what this exponent is. Limit as x approaches infinity of x times the natural log of 1 plus 2 over x. And what we will do is we will write this as a fraction. I'm going to move this x to the denominator, making it x to the negative first. So we'll have the natural log of 1 plus 2 over x 2 over x divided by x to the negative 1. So we're going to try taking derivatives using L'Hopital's rule. Keep that limit as x approaches positive infinity. So I'm going to focus on the bottom first using the power rule. So the negative 1 is going to come out front, and it's going to be x to the negative 2. In the numerator, I'm going to have to worry about doing kind of a chain rule sort of thing up there with this natural log. So I'm going to write it as 1 over 1 plus 2 over x, because that's what the natural log's derivative is. Then I'm going to multiply it by the derivative of what's on the inside. Well, that 1's going to turn into a 0. And I could think about this 2 over x as 2 times x to the negative 1. So that's going to give me a negative 2x to the negative 2 as I'm multiplying. Fun fact about this one, and I think this is kind of cool, is that we've got x to the negative 2 in the numerator and in the denominator, so they cancel. We've got a negative in the denominator and a numerator, so they'll cancel. 2 divided by 1 is still going to give me 2. So actually where I'm at right now with all this simplifying is we've got this 2 left over 1 plus 2 over x. And if I think about the limit as x goes to infinity, this thing's just going to turn into 0. So it's going to be 2 over 1 plus 0, which is going to give me 2 over 1, which is 2. Again, I don't want to leave that as my final answer because, again, this was an exponent. So I'm going to come back down here and write this one more time. Limit as x goes to infinity of e to the x ln of 1 plus 2 over x is going to give me e to the second. And I'm going to leave that as my final answer. That's going to probably be the best answer here because that's an exact answer, e to the second. So hopefully this does help you guys better understand this stuff a little bit more. Please feel free to let me know if you have any questions.